submitted by Zoltan Stranovsky, the lunar dust cloud.
Thank you. So Sascha Kempf unfortunately couldn't make it, so I will be taking the applause at the end of the talk. Nevertheless, Sascha made all of these slides and gave it to me, and Mihai Horányi explained what it means. So, as we all know, in 2013, August, LADEE is going to be launched, and on board LADEE is going to be a dust detector, LDEX, the Lunar Dust Experiment, and LADEE is going to orbit the moon for about 100 days, and is going to provide a detailed map, altitude profile of the dust distribution around the moon, and this is going to be the first measurement of dust clouds around the rocky object. So how is the lunar dust produced and why is it there? And you have heard Mihai's talk earlier this morning and other talks which argue that there might be electrostatically lofted dust above the lunar surface. I'm going to talk about the other component, which is produced by the micrometeoroid impacts on the lunar surface, which is a standard planetary process. So dust production. Micrometeorites are present everywhere, and they impact the surface. Most of these particles, depending actually on the size of the body, are gravitationally bound and move on bound trajectories. Some of these ejecta can escape, and then in these cases, these can feed rings and produce planetary rings, or also contribute to the mass loss of the moons. Further. Okay, so one of the places in the solar system where we can actually observe this production at work is Jupiter's Gothammer ring. You can see the rectangular shape of these rings two embedded into each other, and people figured out that these are tightly correlated with the moons Amalthea and Thebe. These are the sources of these rings, and so the vertical extent of these rings is correlated with the inclination, the orbit inclination of the sources, and these particles, after they are released from the moon, they are traveling inward due to the Poynting-Robertson effect. Ejecta clouds have been observed directly by in situ instruments on the Galileo spacecraft about 15 years ago or so. So all of the icy moons of Jupiter, Ganymede, Europa, and Callisto, have these clouds. And this is the measurement from a couple of flybys around Ganymede. So this is the altitude over the surface of the moon, and the number density measured on the flybys. And there's a power law that I will explain in a moment. So this is really the only measurement that we have, and these are all about icy moons, no rocky objects so far. Nevertheless, we are absolutely sure that these ejecta clouds, which are permanently there around the moons, are actually really there. So is there any evidence for a lunar dust exosphere? And the answer is so far that no, there isn't. First of all, there haven't been that many orbiters around the moon, and only one of them, hidden, was the one that was equipped with a dust detector, the Munich dust detector instrument. However, this orbiter did never get very close to the surface of the moon, and also the detector wasn't very sensitive. So we do not have direct observation of ejecta clouds around any rocky object in the solar system so far. Okay, this is Enceladus, as you might recognize it. Nevertheless, the process is the same for all ejecta particles. So when they are launched from the surface, they travel on ballistic orbits. Most of them, as I mentioned, recollide with the surface. And if you assume that the velocity distribution is a power law, you can actually calculate what is the number density of these particles as a function of height. And there are two two terms here. The first one depends on the velocity distribution of the particles. However, you can notice that for larger radial distances, this goes to 1. This parameter goes to 1. So at higher altitudes, the density profile simply can be described by a power law of r to the minus 5 halves. And d is the index of speed distribution characteristic to the moon and the impact process. As a matter of fact, this simple distribution can describe the measured data well. So these are the density measurements around Europa, including about 8 flyby measurements from roughly 1.5 radii to about 7 from the Europa's surface. We can extend the ejecta model by including the angular distribution of these dust particles. So this work has been done by Sascha Kempf and Miodrag Šemšević in mid-2000. And I'm not going to go into the details how you derive the distributions. Nevertheless, this has been done, and I think it's well understood. This is the distribution as a function of radial distance, velocity, and angle. You see that the number density as a function of radial distance still goes as r to the 5 half power for bound ejecta particles, and for unbound ejectas, this goes like 1 over r squared, which is basically a point source distribution. And the indexes kb, they are describing the partitioning of the energy, how much of the energy of the impactor actually goes to the generation of ejecta. And this angular distribution, if you include the angular distribution, what it's going to change is going to change the shape of the number density as a function of radial distance for small, close to the surface. So they will be of different shape. It also depends on the factor k and the angular distribution, which basically means that if you map out the density distribution very close to the surface and also as a function of altitude from the surface, you can really fully characterize the ejecta clouds. So you can fully characterize the ejecta process, including the partitioning parameter and including the angular distribution of the ejecta process. So and that's exactly what LDEX is going to do on board the LADEE mission. Okay, so how much do we know about the impact facts? I mean, we absolutely have to know how much micrometeorite material is falling onto the moon in order to do this job. So this is mostly based on, I'm sorry for this slide, it didn't transfer very well. So these measurements of micrometeorite influx are based on previous spacecraft data, and also, interesting to note, it's also on the crater distribution measured exactly from samples brought back from the lunar surface. So we know that the distribution peaks at around 100 micron particles, 10 to the minus 9 or so kilograms, and the velocity distribution measured by radars of meteoroids falling into the Earth, and then applied for the lunar case, it's about 17 kilometers per second. So these are the most common particles: 100 microns, 17 kilometers per second. Of course, there will be periods when we have meteoric showers, and during these periods, we expect to see the increase of ejecta particles in the lunar exosphere. So these are the predictions calculated for the LADEE mission. Let's pay attention to the figure on the right first. So this is altitude above the lunar surface. This is hours in time, lunar hours. And the dust density is actually color-coded in this figure. We have the sunrise and the sunset regions. These are the places where we expect the electrostatically levitated dust particles. So that's why we have increased densities there. And the background is basically the ejecta particles. And the impulse line here is one of the assumed orbits, elliptical orbits of the LEDI spacecraft. And if I go to the left side, this is the calculated impact rate for the LDEX instrument. So again, as a function of time. So the line is the impact rate from ejecta particles. So it's going to be about 1 in a minute or 1 in 10 minutes or so on. And from the electrostatically lofted dust, the ejecta rate can be in the order of a few or 10 per second. So really high ejecta rates or impact rates. And as Tobin Monsat in an earlier presentation described, that we are actively looking into the characterization of all of these processes in the laboratory using the dust accelerator facility. So we look at the ejecta particles, we look at the generation of light, ejecta, neutral gas, ion production from impact. So all of these things. And that's basically the summary slide. So ejecta production is one of the standard processes in standard planetary processes. We have good understanding what's happening around icy moons, but we do not have a good understanding. We have never observed directly the ejecta clouds around rocky objects. And LDEX will be the first, or LID will be the first measurement of dust ejecta around the rocky object, around the moon. And since we'll do such a good job, we'll be doing this from an orbit, we will have a full characterization of the ejecta generation process from the altitude profile. And then we have laboratory support measurements going on at the dust accelerator. Thank you.
Zoltan, back on your plot which showed altitude versus local time. Yeah, that one.
Okay.
No, that one. There should be what is a dust density? What is a dust concentration scale on there? I assume that's represented by the color coding.
Yeah.
It would have been kind of nice to have a dust concentration versus color on that.
Mihai, do we have a figure like that? We might have a. Yes, I'm sorry, we are not showing it here. Yeah, it's calculated. I believe this. Yeah.